Okay, then let's start. Hello, my name is Richard Hase, and I will introduce you in this online schooling. And well, first to my person, I'm working for Dlubal for 1 year. Wait, so maybe we can start. You can see me. Yeah, I am working for 1 year for Dlubal, and I work in the product engineering for concrete and also work in the customer support. And I will do this online schooling with my colleague Jonas. And yeah, Jonas, to your person, you can tell something.
Yeah, of course. Hi, my name is Jonas. I'm also working in the product engineering and also in customer support, but my main domain is steel design. And yeah, during the first half of the presentation, I will try to answer your questions as best as possible. And the second half of the webinar, I will be moderating. Yeah, looking forward to this.
Okay, then let's turn the camera off. And before we start, I want to know who of you have the possibility to work with RFEM during this webinar, so that I can see how fast or slow I should do the presentation, so that you have the chance to modeling with me together. Okay, I wait 10 seconds for the last. Okay, the most of you have RFEM open, and so I will reduce my speed, and yeah, so you can design with me. Good. Then, if you have questions during the presentation, you see in this panel, this question panel, and yes, Jonas will answer your questions in the first part, and after the break, I will continue. So, and if there are questions open, we will answer it later. Or if you have other questions after the presentation, you can every time write us an email at info@dlubal.com, and yeah, our support team will help you. This is the first part of the events. So today, the students' member design. So all what you learn today, it's equal for RFEM 6 and R-Stab 9. So because it's only for members, so it's the layout and the program structure is nearly the same. Then following our section program, it's for our sections, so you can create your own sections and calculate them following the RFEM with surfaces. So that's I think one of the big difference between RFEM 6 and R-Stab 9. So, and this you will see on November the 8th. Yeah, the surface calculation. And also we have steel design, reinforced concrete design, and timber design. All events are very interesting, and yeah, if you want, you can register, and it's also for free. So you want then do this. It's a good schooling event. But today for our training, the points I will introduce you on the user interface, so that you get to know how RFEM works, which possibilities you have, which buttons you can click to come to the aim. And yeah, at second, I'll make a little example with a single span beam and show you some things on that, following two other examples where I also show other important content. Then we will make a break. I think I will need 1.5 hours, so nearly. And Jonas will continue with the influence of second order theory, and here the linear bifurcation stability analysis, and will show you a little deeper stuff. Yeah. So, and about the deeper stuff, I want to know how far you are in your studies, so that I have an overview. It's for our information, so please give us this, then we can see. And yeah. Okay, we'll wait 10 seconds. Okay, so we have from every part some viewers, so I think everyone can learn today something. It's a good mixture. Okay, then let's come to the user interface. In this picture, I only want to show you the names. So, but I will in the following, I will show you this different parts on the program. That's more interesting, and you can, yeah, it's not so boring. So good. Here we have the navigator. Here you can design objects like nodes, lines, members, surfaces, and also can loads and all designing objects, I say in short. Okay, then we have the toolbar. The toolbar, you can, or you have little icons, which is for a better workflow. So all what you can design in the navigator, it's switched, or you can put it here in the toolbar. So it's good for the individual and faster workflow. So it's very nice feature. Okay, and the menu bar, you can open and export, import, and you can set the views. The calculation button is here. So, and you also can design, like in the navigator or in the toolbar. It's also possible in the menu bar. The view cube and the workspace, I will show you then in the program. It's, the table, you also can create objects in the table, and the table is very important for the designs in, for example, in timber, steel, concrete. So this table, yeah, have most sense in this direction, I would say. And the status bar give a little information text in the left corner. And yes, then maybe, or I should wait, then I will show you on a program. Yeah, of course. So here the nodes, lines, yeah, what I said, or I decide another way. Let's switch to the first example. It's better, not so. Yeah, yeah, let's do it. Okay, so we have here a single span with an lonely load, and then at the end we want to see the support reaction, the internal forces, and the deformation. So, and I will show you this. Okay, so there, that's our workspace, and here we can maybe wait. We have the axis system, and for this I will show you or delete this, or so. Then I switch back to the navigator. So yeah, how I said before, here you can create the objects. Then we have here another button. It's the navigator display. So all objects you designed before, you can activate and deactivate it here in the display. And for example, the mesh and some results you can deselect, select, or like here the coordinate system, you can number the lines. It's very good for the printout report, so that you can say, okay, my beam 30 is there, and yeah, okay. Also for rendering, different options. Then we have here the navigator views, and it's very good when you have, for example, a building with 2 or 3 floors. So you can say, okay, show me only the second floor, or show me all beams, show me beams with these properties, or however you want. You can generate your wished view. And then when we calculate something, we have here another button. It's the result navigator, and there you can deselect and select the results. So it's for a better overview, but let's start. So the single span have a length of 7.50 meters. And let's start with the simple, with the nodes. So we go here to the 0 point. And now our first problem comes. You see here 5, 6, 7, 8. So the 7.50 meters is very difficult to catch. So you have 2 different options. You can look at this grid point spacing, and the default setting is 1 meter. So we could set it on a ½ meter. So when we go here, you see we could go find the 750 direct, but I will switch it back to the settings. Okay, so and the other option is when we are here on 7 meter, then we can click on this node and say, okay, we want to switch it to 7.5 meter, and then the node is here. Good. Then a beam, or later also surfaces, are or you must generate lines, and these lines get properties which make them to a beam, or the the lines of a surface. So let's create a new line here from node 1 to node 2. And this line is only a graphic line, so don't have I say a really function. It's only the graphic. So okay, then let's make this line to a member. And when you double click on this line, you see here the member. And I say all RFEM is structured when you have a little writer there only, and you can edit these options. And you see here, when you edit these options, more options come here. And so the same is here for member. When we click it, then open the member menu. And yeah, we have a lot of member types. The beam is the default, and the beam transfer all internal forces. So later I will show you, for example, a tension member, and you see only normal forces, only tension forces can transfer. And yeah, but I will show you in another example. And even for the study, there we have interesting member type. It's named definable stiffness. So in this stiffness, we create a new. You see, you can edit all parameters you can think for yourself. And yeah, but let's stay at the default settings, the beam. And yeah, then let's go here to the section. And then you see here, create a new section. Then you spring to the library. And you see we have a lot of options, so which are parametric or in a library. And the next event I tell you before from our section, you can create this section there and import. You have the option to import then the own created sections also in RFEM 6 and RStab 9. But let's take this all. Let's take a HEB 200, for example. So now you can create a new material. And we take the steel. Let's take the 355 European steel. And if you click OK, you see here the section gets this blue color for the steel. And click OK and OK and OK. So now we have created our first member, and you can do it in this way, or you can create it before in the navigator. So you can here make a new material like I showed you before, or the sections, and also you can do it over the table. So you have different options to come to the same aim. Okay, so now we have a single load which we want at 4.50 meters. And now we have different options to say that we can a node load. And so wait, here I say the display mode we can change. So we have different, so the solid model, you see the sections, and can also do the transparent. So what we want to say in the wireframe model. And yes, so now to the options, you can right click, say to the member, divide member, distance, and now you have two options. So I show you both opportunities. Then we say 4.50 meters and divide it. So now we see, okay, our beam have divided in two pieces. So it's in some cases it's good, so that when you want to make separate systems, but in our case it's the wrong method, because we won't have this one beam at once. So then I control and that, and the better options is when you double click on the member and choose nodes on member. Here again the new option. Here the default setting is in %, but we want it in meter. So click it here and say 4.50 meters. Okay, so you see the member is not divided. So it's even very important for the designs in later in the add-ons like steel, timber, and concrete. Because when you separate the beams, every beam must get the special options. So, and when you have this node on the beam, you must only one time say the definitions, and yeah, that's a big point. So then let's create the nodal support. You can do it over the toolbar, or you can do it over type for nodes, nodal support. But my favorite is to do it over the toolbar. So, oh, I forget. It's a test. I forgot it at the begin. So at the begin, we can hear a base data, and there is a type of model. So, and the default setting is 3D. So, yeah, you have different effects which come when you modeling in 3D. So, and some of these effects like torsion we don't need here. So we change it to 2D, the plane stress, and change it. Okay. So now we have a 2D calculation, and yeah, no problems with this 3-dimension. Okay, so let's design the nodal support. There, let's create a new nodal support. We want here for the U direction and the Z direction, and we want fixed. Okay, then we can click here, select nodes on graphic, and say, okay, we want to pick our node number 1. Okay, and want a new nodal support which isn't fixed in the X direction. You also see it on the picture here, so it's more clear then, but we don't need this, only in the Z direction fixed. Okay, and want it here. Okay, so then to the loads, I go back to the navigator data, and every time you open a new model, there is the load case self weight activated. Right click and edit, and the active self weight is activated here. So you must remember that when you calculate it, it's all time activated. So okay, and I show you the difference. Oh, on this example, okay, we go to loads. I want here create a new nodal load and say 10 kilonewton on our node in Z direction. You can see it here. Okay. So, and now we have different options. We can click it here for calculate all, or we go to calculate and click it here. So let's do this. Here, the load case number 1, and to the combinations I come later in the next one of the next examples. So, and now we can control. We have our 10 kilonewton, and one see here the support reactions. So, and now we see, okay, we have our 10 kilonewton, and here we have 6.3 and 8.3. So it don't fit. So what is the reason for that? You remember I said the self weight, it's automatically activated the self weight, and then we can switch to the navigator display, to the loads. Here you see the loads, and activate the self weight. So you see our, what was it, HEB 200 have a self weight, this 1.613, and so yeah, when we only want a calculation without the self weight, and let's check the support reactions, go to the loads again and deactivate the self weight and calculate. And now you see we have the 4 and 6 to the 10, it fits. So so you must remember that if you want to make a control, that the self weight is activated or even not. Okay, then when I say at the begin, the navigator results, you see we have calculated, and now we have here a new button of the results. And yeah, you see here the deformations, the maximum deformation, but you can also, when you go to deformations, wait, where is the maximum? Yeah, here on member, you can say, okay, show me all values. Ooh, this was for the moments. Yeah, so So you can say, okay, give me only the maximum moment, or show me all values. So you can click it in the navigator results, but we stay with only one result. Then you can show under internal forces shear forces, and yeah, okay, the other are 0, stress and strains and stresses, and support reactions. So you also can do a resultant. See, okay, 10 here fits. Okay. Good. Then maybe I switch a little fast about the toolbars and the menu. So I will come to that yet. To the menu bar, you see you can here open a model or make a new model. You can save it, print it to PDF, edit. You can say, okay, I want to have other units or decimal places. And global parameters, I will show you in another example. It's also a very nice feature. You can hear the view. You can also, when you say, okay, the table I don't want, you can deactivate it. And when you click away, for example, okay, navigator results, oh, I don't want it, then you can, on the view, you can reset the menus and toolbars. So that was what I mean. Restore default layout, so you get back the standard view. Okay, yeah, then you also can create objects, line supports, for example, or here's a nodal supports. You can do it also in the menu. Calculate, I show you results, different tools, display properties. So you see the white background. You can change it here, for example, go to dark background. It's your view, the standard view, but it's better for the presentation with white background. Okay. Yeah, then to the toolbar. I showed you before, you can have the nodal supports here. You can create lines, members, loads, and show the deformations, and nearly everything you're searching for, you can do in this toolbar. So, for example, what I will show you later, the global parameters, but let's show on this example, you can customize your menus and toolbars here. You can say, okay, give me the global parameter, and then you can pair drag and drop. You can add it here in your toolbar, and is for every function is it possible. So you click it here in the search function, and pair drag and drop, you can customize your toolbar. So feel free, which workflow you like, you can create it. So okay, then I think that was for the beginning. Okay, then let's switch back to the PowerPoint presentation. Yeah, now we want to see a 2-span beam with altering load positions. So we have 3 load cases, and the task or the aim is that you can see, okay, which combination of load cases give me the maximum field moments, for example, or the maximum nodal support force. And yeah, I will show you this now. So then we click here on new model. Okay, then let's take 2D again. It's good for our model, and say two-span beam, for example, to the add-ons and standards. Yeah, you will see it a lot in the coming events, but only for informations. So you can click it here, for example, the concrete design, and when it is activated, the beams and, for example, also the surfaces get extra options you can select, so that you can do the design check for concrete, steel, timber, masonry, aluminum, and so on and so on. Also the standards, for example, we activate concrete design here. You see, okay, on which standard with here's the ACI or Eurocode, and which national annex the calculation needs, so you can select here. Okay, and the other, it's not so important at the time, and you will see it also in the other events. So let's deactivate. But okay, new model. Okay, yeah. Before I show you the model with the node setting, then the lines, and give these lines the property of a member, and you can do it in a such faster way. So you can create here a new single member, or can do it here. But let's go the other way. I want to have another material. So let's say I want a new material. And yeah, you have the option I show you before, that you can here, for example, select a region, and then the material type, and so on and so on. So that's the first option. Or when you don't want to search it, you can do it with these two signs. And I searching for S235 steel. So, and when you see, yeah, then the program search all the library after this searching word, and you can select. So I wanted for new the Eurocode norm. Okay. And okay. And the option also functions for the sections. So when you click new section, so you say, okay, I want HEB 300, or maybe so in this way. Yeah, the HEB 300. Let's here's the Euro norm. Then you see it. Okay. And okay. Good. Then yeah, let's create a new member. Beam fits. Go to the section and select here. Oh, wait, then we go back. Sorry. Yeah, we have here our HEB 300 with the wrong material. So we go to edit and say here, material, we want our S235 and okay. Then we want the HB300, okay, and say okay, and go to the 0 point, and yeah, 10 meter it fits. And we also can do a node on member over divide member distance, and then you must click this this option, create on member nodes without dividing. So that's what we want. And the half, okay, and okay. So yeah, we have one member, and we need our nodal supports again. The fixed one, we take it here. Okay. And once the roller, you want, oh wait, I want to show you why it don't. Okay, okay. Yeah, and if the nodal support is too big or too small, you can right click and can here change the size. So, but I think this size it's okay. Then let's add a new support, a roller. Okay. And okay. So, yeah, to the view cube. So, you can press the control button and the middle mouse button, and then you can change the view in this direction. Or if you say, okay, I need a fixed view, for example, in the Y minus direction, then you can click it here and you come there. Or you can use the view cube is the same, and so click here and can change in every position you want. Okay, but let's go to the load cases. We want to make a new load case. So we have the self-weight, and then we want another load case with the action category and post loads category A, and say it's the load left side, and we can create a new, or we can copy this and say load on the right side. Okay, so now you see the different action categories. So we have permanent and imposed loads, and the default setting is that you have activated the combination wizard. So when you have this combination wizard active, you see that the program automatically do combinations of the loads. So, but for that you need different action categories. So you see here, and then you can choose different types. So you have this option, so it's all-time active. The alternative type, special for wind, for example, when you have went from the left side, from right side, from top, from bottom. So you can say, okay, this wind loads never come together. So then you have this alternative action type. And when it goes more complicated, you also can say there's a different type. Then you can give the load actions different relations to other, but yeah, we let it this way. So then the default setting, we have here this free, and you can see here over informations the combination rule. And after this combination rule, you see the action combination. So action combination with the B5 combined with the action 2 with 1.5. And out of these action combinations, the program create the load combinations. And yeah, okay, only for overview, but we say okay and want to generate the loads. So we say for our load case 1 self-weight, go to member loads, say we want a new member load, and we want 2.5 kilonewton per meter over our member. Click OK. Member 1. Okay, so you can choose the OK button, then the member load close and you have your load. But when we say OK, we want switch to the other load cases and generate there also loads, then press apply and next. So you also see our load, and now you can switch to load case 2, where we have one load on the left side. And now we need another load distribution, trapezoidal. And okay, we need here also, you can see on these pictures the load sizes and the distance. So okay, we want here 5 kilonewton, 5 kilonewton, and want it from begin, from 0 to the middle, it was 5 meter. Okay, and here our member 1, say apply and next. And now we switch to our load on right side. Again, member number 1, and now the A is 5 until the end of our beam, the 10. Okay, and when we're ready with all or finish with all load case entries, then we can click OK. And now you can control it. Here is the self-weight, including the self-weight of the beam. We can deactivate it again, but have it, don't forget it. And yeah, here the left load on left side and the load on the right side. Okay. Another thing, when you want calculate with a book example, for example, then you must remember that when we go to the sections, we have here shear stiffnesses, and in the most books there are not thinking about it and let it away. So if you want the exact results like in the book, so you must deactivate the shear stiffness, and through this button the shear stiffness will be infinity high. So in this case you have a lower deformations because more stiffness in the shear factor. Yeah, I will show you the difference. We let it deactivate it, and then let's maybe for the self weight we show you. Okay, then click it, show results. Okay, and maybe we can deselect the loads. So now we have here the 1.0.2, and when we go to the sections back and activate the shear stiffness, so then okay, then it deletes the results, and let's calculate it again. So you see it's changed from 0.2 to 0.3. So the deformation is bigger because yeah, the shear stiffness is making the system softer. So yeah, you must when you make control calculations with literature or so, then most time the shear stiffness is deactivated. Okay. Yeah, then okay, let's calculate. Well, again, I say something to the combinations, and for example, for the ultimate limit, these four load combinations give their internal forces to the design situation. And so, yeah, let's calculate the design situation, and then I show you what I mean. So see the load combinations, and now you have the option to show you the max and the min values. I'm switching to the wireframe model again, and okay, to the bending moment. Now you see, okay, you have two, or I'll show you before the max values. So the maximum values is the most positive values. So we have here the 26, and here the minus 15, and in the minus is the biggest minus value and the lowest positive. So okay, and now we say I want to know from which load combination come these 26 kilonewton per meter. So then you go to this table to results by member. See here global deformation, local and internal forces. Click to that. Member number 1, that's right. And see here our my moment. the 2675. So, and then you see the corresponding loading. See, it's combination number 2. Combination number 2 was here. The self-weight plus the load case on the left side. Here is the load case left side. So this combination gives the biggest moment on the left field. So then we can check this moment, the biggest minus, and it's here, the minus 37.95. It's from combination number 3. And we go back and see combination number 3 is a self-weight plus the left side and the right side load. So yeah, you can see and understand where the internal forces comes from. The same is for the support reactions. And now we want to know where come the 77 kilonewton. Then we must only change here from results by member to results by node. And then you see that's on node number 1, node number 3. Okay, then support forces, node 1, 2, and here node number 3. See here our 77.45 also from combination number 3, and it was the safe weight left and right. So okay, then what I want to show you. No, that's okay. That was it for this example. And before we go to the next example, I want a little poll about the shear stiffness. And I hope you remember it. What is the effect of neglecting member shear stiffness? And okay. Okay, the answer would be that the deformations tend to decrease. So because just the shear stiffness factor, when you deactivate it, it goes to infinity. So it makes the system more harder, I say. So yeah, the answer would tend to decrease. Okay, then let's here we have a Gerber beam, and the Gerber beam, so you see here you have the same field moments and the moments on the top side. So it's a very similar system, And so in Germany we have a book. It's with special formulas and so, and yeah, so we want to parameterize the structure that we all time have the distance, that we have the same moments. And how you do this, I will show you now. Okay, then let's make a new model, and we call it Gerber beam. Again, the 2D. And here we have again the same. So maybe I can do it a little faster. Okay, make notes on member. 50%. Okay. And say we want here our hinged and need here roller here and here. So, and now we want the hinge in this area. So this, oh wait, I can add a dimension from here to here and here. So 5 meters every side. So, and our Gerber hinge is nearly here. So let's say, okay, we divide our member for distance of 6 meters. And this time we won't separate the beam because the Gerber beam have two different parts which are linked over the hinge. So it's statically determined system. So, okay, let's separate it. Okay, it's good. And then let's come to our global parameters. You find it under structure and here added global parameters, or at the beginning I show you, you can also switch it or transfer it to your toolbar, and yeah, it's the same. So I started the parameters and call it length. Let's say 5. And we want the hinge. And this was from the book, the factor 1716. Yeah, you can hear the unit group change, but it also function when you let it this way. Okay, so on this name you give in the global parameters, you can use it in the formula editor. And how you do this, I will show you. So, okay, this point is fixed. And now we want give our node this formula. So make attention, here is a percent sign, and our global parameter is in meter. So then you can click on this little triangle and click here, edit formula, and say, okay, the length is 1 time the length. Okay, you see our global parameter, and the result is 5 meters. Okay, Okay. Now our other node, we want to do the same. Again, the triangle, edit formula, and say 2 times the length. Okay. And okay. So now what is missing is the hinge. And yeah, we say it's 6 meters, but we want exact. So we go to edit formula, say length plus hinge to the length. And now we have the 5.8.8 meter, and that is the value from the table. And we say okay. Then let's do again a dimension that we can control it. Okay, go to second plane. So 5 meters. And when we now want to change the global parameter and say, okay, I want to have field length of 8 meters, then it automatically change the length. And now I want to show you the effects of the moment. So we take the self-weight and let us show the results. And go to the moments. And okay, I forget the most important of a Gerber beam. It's the hinge. Sorry. One moment. Yeah, and we must create a rotational hinge for the moments. And click OK. And click OK. So you see the little white one here. We can also with right click make it bigger a little. Okay, so then let's do it again. The self-weight start. Okay, so now we have the dimension. So we have 6.4, 6.4, 6.4. And when we want to change back to structure, global parameter, and say, okay, the field length of 5 meters, and calculate it again. Then we see, okay, the hinge distance automatically fit to the length of the fields, and we see the moments 2.5, 2.5, 2.5. So the parametric systems is a very nice feature, and you get it with these global parameters. Okay. Then let's see. Then I have one last example. It's a 2-hinged frame with tie rod. In the examples before, yeah, I have the beam which transfer all forces. And now I wish you attention type. So, and yeah, I will show you how you can create that. Then let's make a new model. What was the name? Oh, let's call it frame. Okay, the 2D plane stress again. Okay, to the Y. And yeah, we take again the same members in the beam type. Okay, and say we go to the 0 point and 5 and go E5 and 1, 2, 3 and connect it in this way. So, and now if we had a mirror here, we have the exact system. So let's do it with the mirror selected objects. So you click here, you want create a copy, and the mirror is in YZ, and then you choose one point. Let's choose this one, and when you say OK, so when you have symmetric systems, you can be clever and make one half and then the other half make it with the mirror function, and yeah, it gives a little time back. Okay, then again our nodal supports. We take the hinged. Okay. And want it a little bigger. Okay, so then we want our special member, the tension. So again, here the beam, all internal forces were transferred from the end of the beam. And now we take the tension, and only positive normal forces will be possible to go through this member type. Okay, then let's do it here. And so it looks very, well, it all looks similar. So, and you have the options when you go to the navigator views, members by type. You can say, okay, show me the beams. Then you see, okay, this one, or show me the tension. That's one option. And the other one is when you here under in the navigator display and in the object property, go to members. So the reason why all look same is because it's choose the material, and you can change it to the member type. And wait, we must cancel. So yeah, it's near the same color, but you can change it to yellow, for example. Then you see, okay, you have the blue one, the beam members, and the yellow one is the tension. Okay, but let's go to a wireframe and add some loads here. So let's add some loads. You can load a new load case here, or also in the toolbar. So when you see okay here, the new load case, Then we want snow with the action category, snow ice loads. Want a new, and this should be wind from left side. I have here the wind, and a new one, let's say temperature. Okay, so and now we see again the action categories. So wind, okay, now we have only one wind load case, but it's the default setting because, yeah, I tell you before. So the design situation is same, action combinations. Now you see when you have more than 2 load actions, then the normed combination rules. When you look here, so you have here the gamma values, which are the same, but the psi values, yeah, you can see different psi values and which is the leading load, and yeah, you can see it. And the load combinations again the same. Okay, then I don't have okay, I don't have click OK. That was my mistake, so it broke up. Then again, fast snow, wind, and temperature. Okay. Yeah, then let's create some snow loads. We go to member and say snow load. Yeah, and now you see on the picture, it's not a typical view for a snow load, so you can create a change it here in the global and set. So that's typical snow load looking. Choose these 2 members. Okay, let's say simple 1 kilonewton per meter. And let's go to the wind. Yeah, here we have another. We must choose the local. So that's typical for wind loads. And choose all members which get load from, okay, from left. So these 2 are correct, and these 2 should go in the other correct direction. So you can double click, take a minus on that, and it changed. And here same, and change. Now, yeah, the wind load looks correct. And now the last one, the temperature load. Let's take a member load. And now we have again some other type. It's the temperature change. And let's see, say here 35 degree on all members. Okay. This yellow is terrible. Let's change to red. Okay, so and now we see the effect of the tension member when we, or you can calculate all, or in our case, let's say, okay, we are interested only in the load cases. It's enough for this. Then you can select it, solve. Okay, then we want to see the normal forces. go back to self-weight. So with the minus is pressure, and the red one with the plus is tension. So you see the self-weight here, you have pressure, normal forces, and here we get tension. So for snow, nearly the same. And now we have the next load case is the wind from left side. And now you see here we have tension, here pressure, and you see here there's no force because you get pressure here, so it falls away. Don't have an effect here, and yeah, that's what we want. And okay, temperature the same here, tension and pressure. Okay, I see here I have the wrong section. Let's correct this in the fast way. So can hear the massive one, the parametric. So and say with a 50 millimeter. Okay, so the results are the same, but only for correctness. Why is it? Oh, it's now I have changed all members because I. Okay, again, one moment, members, edit, and say here. So now I have corrected. Okay, yeah, the tension member with the circle section and our HEB profiles. So now we are correct. And I show you the effect of the tension beam. And yeah, at the end, I want make one last poll. And after this, we can make a little break. And my colleague Jonas will continue after this break. But let's do one last little poll. I will start. The question or the sentence is: beam members transfer all internal forces. And is this true or false? Okay, I wait 10 seconds more. That looks good. Okay, yeah, everyone who does give an answer was right. The answer is true. Beams members transfer all internal forces. That's right. Okay. Then yeah, let's go into a little coffee break. I would say 10 minutes should fit, so that we see 35 again, and then Jonas will continue the online training. And okay, and in 10 minutes we see again.
Yeah, hello and welcome back to the second part of our student online training of today. My name is Jonas Bien and I would now like to continue. I hope that most of you are already there. I saw that we missed out on one of the polls, and I can use this as an opportunity to check how the activities are, if there are already people behind the screens. So I will just start a poll. So it's a basic question, and if you have a good memory, you will and now have a bit of experience because you clicked along for the last few examples together with Richard, maybe it is an easy question for you. But yeah, let's start the poll. So the question is, where can I create objects such as nodes, lines, and so on in RFEM? So there are multiple options you can choose from, and you can select multiple at the time. So first answer would be the menu bar, the table, navigator, or the toolbar. So I see that nobody is voting so far. Okay. Okay, so not a lot of participants. I would leave the question open for 10 more seconds, and then it is as it is. We will continue with the webinar. Okay. All right, so I close the poll and yeah, show you the results. It's I think just one or two persons voted, and the right answer would have been everything. So you can use multiple ways to define objects in RFEM and also RStab. So in this case, all possibilities would work out. All right, so let's continue with our examples. I've prepared some additional ones for you. The next one would be this suspended single span beam. So we see a blue bending beam here in the lower end of this example. The total length of it is 16.5 meter. And it is suspended in its thirds. So there are truss members that in this blue nodes act as an effective vertical support. And we have a distributed load Q equal to 15 kilonewtons per meter acting on the beam. And we should determine the support forces and internal forces. And I want to show you some additional viewing options. All right, so I see that people were not able to pick multiple answers in the poll that I just started, so maybe we used the wrong settings for this particular poll. So that's then our fault, and I would like to excuse that. All right, let's jump back into RFEM. I basically also created an empty model. It's the same assumptions as Richard already had or introduced. So we have a 2D model, nothing, no add-ons or anything activated. I cheated a bit, so I created the steel material S235 and one section because Richard already did that and I don't want to repeat. And yeah, thus I can directly start to model our beam. So I will just do that. So I generate a simple member. Member type is beam in this case, and the section should be HEB 300. I confirm these settings, and then I click on the origin, and I want a beam that is 16.5 meters. And now I forgot to change my points in my work plane in the grid, so I can only pick 16 or 17 meters, so that's a pity. So I could have done that on beforehand, but I could also use the direct input of the second nodal coordinates in order to set my second node location. So I can also enter 16.5 meters here for the x coordinate of the second node and 0 for the z coordinate. I just have to make sure that I don't hover over the workspace with my mouse now. Otherwise, the coordinates would reset. And if I now hit apply, my beam is generated. Okay, we can see it has the correct section. Everything looks fine. Now I want to introduce 2 additional nodes on the member. So I divide my member with the function. So I right click, then the context menu opens, and I want to manipulate the member. So I hover over members, go to edit. Oh, sorry, that was the wrong function. I wanted to divide the member. Members, divide member with n intermediate nodes, and I want to have 2 intermediate nodes with equidistant distance. And as Richard already showed you in the beginning, I want to use member nodes with the type on member without dividing my beam. So I get these 2 additional blue nodes here. I will switch to the wire, the draw wire view, so you can better see this. And then I introduce supports at the beginning of the beam. Wait, let me just get rid of the coordinate of the axis system and the origin, so we can better see what's going on here. And then the second support is a sliding support in X direction. So that would be this one. And I assign it to the end node of my beam. All right. Now I have to, or I can also, now that I have the beam, I can apply the member load first. So I choose to apply a uniform member load of 15 kilonewtons per meter. Assign it to member number 1. Okay, so that's already done. I can do the same as for the supports. I can just open the context menu for that load and quickly adjust the height if I wish so. So I think it was a bit big, so I just scaled it down a bit. And now we have to model the suspended part of the beam. We can also, if we want, we can see how it influences the results. So if I calculate quickly without the suspension, we can analyze the deformations and then later compare what the suspension does for us. So you can see there are quite large deformations of 276 millimeters. So that is probably not okay for the design. Nobody wants such large deformation. So we will see what we can do with the suspension. To make it easier to model the suspension, I will just copy the 2 nodes on the member upwards, and I think we had a delta Z of minus 1.4 meter. I create a copy of these 2 nodes and hit OK. And now the program automatically sees, okay, these nodes that I want to copy are not on the member anymore, so it changes its type to standard. I do the same with the nodes at the start and the end of the beam. Now I enter 2.3 meter as a minus delta for my Z direction and also hit OK. Now it also copied the supports, which is okay. In this case, I just need to change the nodal support of the node in the upper right corner to a fixed support. Otherwise, we will have an unstable system. And now I can use these nodes that I pre-generated to just enter beams, or in this case I want to use truss members that only transfer normal and vertical forces due to self-weight between the nodes. As a section, I'm not sure, but I think it let's see, should be an IPE 200. So let's quickly define a new section. We can simply do that by putting the name of the section we want to use here, and we get it in the quick search. I will just choose one of them and hit OK. So now I also have the correct section for the suspended members, truss members, and now I just add those to the model by adding them between the nodes I just generated. Just the vertical members now. Okay. And now it looks pretty fine to me. I can show the volumetric rendering, and also what helps is to maybe plot or color it by section type. I will do so that now I can make sure I have applied the correct sections, and also I can check the member type. It's also fine to me. And now I hit the calculate button, or I ask the program for results, and it realizes, okay, there are no results, so I have to calculate them. And now we can see we have vertical deflections of 46 millimeters in as a maximum deformation value, which is much less than we had without the suspension. So before we had 276, I think. So that's they do contribute a lot to the vertical stiffness of the system. We can also show the deformation of the member of the members on colored sections. So we go to deformations. These are some of the results settings for the view settings, and we change the deformation view to section colored. So that gives us a good information and good idea of the deflections between the nodes. And it also has the benefit, so if we have some rotations of the beam, in this case we don't have, the beams don't rotate around their own axis or the local axis, but we could also see it when we change the deformation view to this mode. That's another advantage. Okay, then let's check how the internal forces look like. We see that these truss members here in the suspended part, they take huge axial forces in tension, and we can also check the moments, bending moments. So we don't have any bending moments in the truss members as expected, and in the beam we have like yeah, it looks yeah, like we have 3 different parabolic shapes here. And we now only see the maximum bending moment value for the intermediate field, but if we want to see the maximum values of this or this parabola, we can also add additional result values. So for that we go to the settings here and to members, and we say we want to see all values, and this way we can also see how the maximum bending moments are in the left and the right field. All right, we can also yeah, do a close or give it a closer look to the results of the bending beam if we click it, select it, and then we see just up here we have the possibility to show result diagrams for the selected member. Let's do this. And what we now see is the results over the length of the beams. Or we can also see where the position of the intermediate nodes is along its length. And we can check multiple results in one view, so we can add additional result values here, so we can also analyze the vertical or the shear forces here in the same window, and we can seamlessly hover along the length of the bar, and we get the interpolated results for all result values that we have activated here. We can of course also plot such result diagrams to the printer, to PDF, or to our own printout report, which is used for documentation of designs and calculations in RFEM. All right, so that would be already it. We could, of course, also, what is interesting are the support reactions. We have quite large support reactions in these upper nodal supports here. Of course, they correspond to the large normal or actual forces in the truss members. All right, so that would be it for this exercise. Let's move on and get to a new topic. Now I want to speak with you about truss members. So I delete everything that I modeled here and show you the next task. So next we should model an ideal truss structure that you can see here. We should use truss members with only N. So these only transfer normal or actual forces without considering any gravitational loads that could otherwise be transferred. We should use for all members the HEB 300 that we already generated, and we have some. So this truss is simply supported at the lower chord, and we should also apply nodal forces at the upper chord. And the task is to determine the support forces, internal forces, see which members are in tension and compression, and which are basically null members and can be neglected in the structure. So let's do this. Note that the length of all members should be 3 meters, at least the ones belonging to these outer triangles. Okay, so in this case, if we, for example, want to start with the diagonals, and we know the length of the member and the angle, so it should be 60 degrees towards the x direction, we can use the function, you can find it up here, a single and work plane, and this allows us, after I set the member type and the section to the correct ones, this allows us to define a member by its length and the orientation in the work plane. So we can see an orientation of 0 degrees corresponds to an orientation parallel to the z axis and in z direction. So we want to have an orientation 60 degrees towards the x axis. So we need to enter for alpha 90 plus 60 equals 250 degrees. We can also input this here if we don't want to calculate it in our head. Yeah, it gives us 150 degrees, and we can enter the length 3 meter, and then we have an annoying little bug right now, so we cannot select the origin for some reason, but when I deactivate some of the snapping options, I can set my first member, and then the next one I want to do the opposite, or define in the opposite direction. So I add 60 degrees to it, and that looks like this. And now I could also define the last member of the triangle when I enter 90 degrees for alpha and connect the two lower nodes. So that leaves us with the first triangle of our truss structure. And yeah, now I want to show you another option, how we can copy single objects or selection of objects. In this case, I select all objects that I have defined until now. Then I move my cursor close to the lower left node and hit the Control and Shift button at the same time. And that lets me drag and drop my selection, and it automatically copies it. So when I drag this triangle with the 3 members and the 3 nodes here and connect it to the lower right node and now release my left mouse button, then it copies this triangle and we end up with 2 of them. I can do the same now again with the second triangle and copy it to the right of it. So that would already be all the lower triangles that we need for our truss structure. We can also use the drag and drop function to generate our upper chord. So I can just select my one of the lower members, or I can also select 2 of them at the same time. Again, press Shift and Control and copy them to the upper chord. So that would be all the chord and diagonal member. And now we only need to define the vertical members, and this is also quite easy. We can use the simple single function to create the last members. And I will define the first member here on the left with the upper node, and then I go down and you can see by default we have a snapping point at the half of a beam length, yeah, and I can just snap this half point of the lower horizontal member to generate my vertical member. And this one I could also copy with drag and drop, or in this case I need to do it 4 times. It would be a bit more convenient to use the move copy function. So I could do 4 copies at the same time. I just need to set the displacement vector correct. Of course, I need to make sure to hit the create copy option and introduce or put in the number of steps. And then I define my displacement vector graphically by selecting 2 points. And then the spacing is automatically determined. It's just in the global X direction. So that seems okay to me. I hit OK. And now I see that all the vertical members I needed are generated by this copy function. Okay, then we are left with the supports. I again, as in the last example, I define a fixed support or roller support, but with free rotation in the lower left node and a sliding support on the lower right. So this roller support type, where I just fix or restrain the Z component. And now the last thing I need to define before I run the model is the member or the nodal loads at the upper chord. And I think on the 2 nodes on the left and the middle node, it was 10 kilonewton, and on the right node it was 20, but I can also apply a force of 10 kilonewtons to all these 3 nodes, and then in a subsequent step manipulate the load at node number 8, just change it from 10 to 20, and I'm basically finished with all the modeling work. Okay, let's see how the wireframe model looks in this case. Everything looks fine, so I guess we can start the solution, the calculation phase, yeah. and analyze the internal forces. We can see that we have no vertical or no shear forces. We have no bending or torsional moments. We only end up with axial forces in this truss, and this is exactly what we want, because we here assume that we have an ideal truss. I did forget to mention what this actually means. It was also on the task, it said we want to model an ideal truss structure, and this comes along with some assumptions. One of the assumptions, or let's just list these assumptions. First, we have perfect hinges between all these truss members, so there are no bending moments that are transferred here due to friction or due to some semi-stiff joint. Then we have no imperfections in the truss members, so they are perfectly straight and can be considered like this. Another assumption is that we have no eccentricities in the joints, so where all the truss member meet. They meet the system lines, they intersect in one common point. So in this case, here at this node, 5 different members meet exactly in this point. That's also not every time the case in real truss structures. And all the loads we define act on one of those nodes of the truss, so we don't have any intermediate loads acting on the members, and we don't have any gravitational load. Yeah, and this leads to those results that we only get axial forces in our truss, and we can now try to categorize the members that we have. So we analyze the normal forces or the axial forces, and we see we have some that have positive axial forces. So these would be the compressive truss members. The positive ones would of course be the tension members, sorry. So it's also indicated by the red color. So all the truss members that have red axial forces, they are the tension members, and the blue ones would be the compression members. And what we see as well is that our vertical members here, they don't have any axial load at all. So these would be our zero or null members, and those under the assumptions that we set and under the loads that we set here would have no functions and could be deleted without altering the results. Of course, we can also analyze the deformation if we wish so, but that was not the task in this case. All right, so as you have seen with all the manipulation options that we have, it's very easy to define such structures, but we have an even simpler way to solve such a task, and this is by using blocks, and that would lead us to the next example. So the next task would be to create a pre-generated truss structure by using blocks. I will just show you in a minute what these blocks are and how they are defined. And so we should generate this and then do some changes to this pre-generated truss structure to see if and how we can do so. So let's start with this. I will again delete what I have modeled for the last example and now show you a new world, let's say. So I can introduce these pre-generated blocks by using the block manager. I could also, so all these blocks are located under special objects and blocks. I could also double click on blocks and create a new block. That also brings me to this block manager. And in here, you can see that we have a lot of pre-generated structures. So for example, single span beams or continuous beam that we have modeled also in this webinar. We could use such blocks to quickly generate those structures, and you can see under the section trusses, we have a lot of 2D trusses already that we could use for our student or any real project. So we can use such blocks to build larger structures. So for example, we could build a whole 3D hall made of steel components just by adding blocks together and calculating it. We have also some more advanced blocks. For example, we have like let's see, we have even tower parts that we can combine to in bigger structures. So that's quite interesting to see. You can also find some predefined stairway structures or something like this. So it's very neat. I think there is one employee at Dlubal that just prepares such blocks for the customer. But the block that we are looking for is actually can actually be found under trusses 2D, and then it would be the first one with the block description FT001A. And the nice thing about these blocks is if we double click it to bring it into our model, okay, we are required to change the model type to 3D, but that's not a problem. Let's do so. So these blocks require a 3D model, but that's not a big deal. We can just change it, and now we can first in the first page see, or we have the option to change the position of where we want to insert this block in our whole global model. Now it's set to the origin, which is in this case fine for us. But in the second tab, we can also change the dimensions, for example, of this object. So we can say, okay, I don't want to have such truss with 6 base. I want to have, I don't know, maybe 10 base. So that's no problem. Just so it's pre-parameterized. I can change this number quickly by putting in different numbers. And for this example, I'm asked to change the length and the height of our truss. So I think 6 base is for us okay here, but I wanted to change, or I'm asked to change the total length of the truss to 18 meter. And all of the base should be 3 meters in length. So I have multiple ways to do that. I now decided to do the input via L and L1, but I could of course also do it by changing L1 and L2. That's preference. But yeah, in this way I set the default. I follow the default path. And the height we want to adjust from 2 to 2.5 meter. Okay, so that would be the dimensions set and done for our truss. Then we also need to change the sections. So for the upper and lower chord, we are asked to use an HEA 300 instead of an HEB. So we can quickly change the section if we want. So let's make our HEB 300 into an HEA. Just change one letter, and here we are. So top and bottom chord would already be perfect. Now for the diagonals, we want to use an IP 160. So let's just use the second section and redefine it or change it from an IPE 200 to an IPE 160. And since we are already here, the posts, so the vertical members of our truss, they should be in HEA 160. I will just copy the section number 2 with the IPE 160 and change it to an HEA 160. Okay. Apply, and then I change the section for my verticals to an IPE, and for the diagonals to the IPE, and the verticals get section number 3, HEA 160. So that would perfectly work out. And now by clicking OK, this block would be inserted into our model, which is very nice. So it's very easy to define bigger and larger and more complex structures with this. And you can see it's still parameterized. And the nice thing now, if I want to change something, I can at any time modify my block. So I can go back to the parameters of the block and change them whenever I want. And these blocks, or you are not restricted to the blocks that we have so far predefined and fed into our software. You can define such blocks on your own, and how that is done can be seen here when we go to the last page of the block. We see the source code that is the basis for our block, and you can see this is written in a certain programming language in JavaScript, and you can first like study all these functions and the source code for these blocks to see how the input for such blocks is. You can combine input from different blocks, and you can of course alter or change, do some slight modifications to the input to learn how this programming language can be used in the context of RFEM. You can also use JavaScript to do in-app scripting. So it's also, you can activate the console and use the JavaScript functions to generate, for example, nodes, and you can also use the console to find out how the syntax for different operations looks like. For example, if you go here, you can find a lot of information about programmable objects here. So that's quite nice. Yeah, but that's a whole another webinar, I would say. I'm afraid it's too complex to cover all of this here, but I just wanted to show you how far you can go with the in-app scripting already. All right, and now our task was to, we can see that these diagonals and vertical members, they are actually members of the type beam, with some hinges applied to them at the start and the end of the member, and we were asked to modify these members and change the member type to truss. So we can just select all of these members and change the member type to truss or truss only N. Click OK, and now we get rid of the hinges, so that's makes it a bit more clear in the modeling. So we get rid of some objects, and we can also, by like analyzing by displaying the member type, we can now already directly see how the members act, what degrees of freedom they have, and which internal forces they can transfer. So that makes it a bit more clear in the modeling. All right, yeah, but we don't want to do any further investigations on this block. I just wanted to show you that the possibility is there to create such blocks and build up your models from those blocks. It's very convenient. Yeah. All right, so let's get rid of all these objects. I also delete the blocks. that I had in there, because now we want to increase the complexity of our used theories, and we want to explore the different static analysis settings. So so far we have only accounted for a first order deformation theory. So we calculated all of our structures based on the assumption that the equilibrium can be formed on the undeformed. The equilibrium can be calculated on the undeformed structure, but in some cases this is not applicable, because deformation will influence the resulting internal forces. This is especially the case when we have slender structures or elements. For example, in steel structures, we usually have quite slender columns, for example, and if we want to calculate them under compression and also some lateral forces, for example, we cannot neglect the influence of the deformations on the internal forces. So I just want to show you how we can take such effects, so a second order theory or the p delta effects into account in our program. It's quite easy, and we want to see on a simple, for a simple example, what influence this has. So now we want to model a simple column that is fixed on its end and loaded with a compressive vertical force and a transversal force, and we want to see how the results are affected when we switch from the first order to second order theory, and how we can do that. So first of all, I have to do the modeling work. It's quite straightforward. So I create a beam member with a length of 10 meter in the origin. I just have to make sure I didn't check the section, but I think we should use an HEB 300 here. So I have to adjust the section number 1 back again from HEA to HEB 300, but that we have done now multiple times, so that shouldn't be a huge task. And then we have to assign fixed nodal support to the member end, or the start of the member. Note that we have now changed the model type from 2D to 3D, so all six degrees of freedoms are now active in our model. They are not grayed out anymore, so that's a huge difference. So in this case, we need to then fix all the translational degrees of freedoms and the rotational degrees of freedom here. And we assign this to our bottom node, of course. All right. So I will enlarge the nodal support a bit. We can also check the model type in the basics base data of our model. You can see that now when we created the blocks, we were asked to change the model type, and we can of course see that here in the base data of our model. We will stick to the 3D model for now. All right. Then the last thing we need is the nodal forces at the column tip. We could introduce two separate nodal loads of the type force, but we could also use the load type component, and that lets us define multiple loads and moments at one node at the same time. So I will use or enter a vertical force in Z direction of 100 kilonewton and 10 kilonewton transversal load in X direction. And this load has to be assigned to node number 2. Okay. And now we see we have the load the load is applied. It looks correct to me. So we could start with the calculation according to first order theory. So I don't do any adjustment to the calculation settings and take that as a reference for further analysis. So we see under first order or calculating this structure under first order theory, we have a uniform or a constant vertical force, axial force in the member of 100 kilonewton. We have a constant shear force of 10 kilonewton due to our transversal force at the column tip. And our bending moment around the strong axis is 100 kilonewtons, which can be easily calculated by multiplying the 10 kilonewton up here with the length of the column, which is also 10 meters. So 10 times 10 is 100 kilonewton meter. We can also choose to show this reactional moment, but we have to activate it separately in the results settings here. All right, now let's see how can we now activate a second order theory and do the analysis according to or taking into account the p delta effects. Therefore, we go into the load case. And here under the static analysis settings, the default setting for load cases is generally a geometrically linear analysis. And we can see how these settings are defined. I just click on the edit button, and we see that we can here change the analysis type from geometrically linear, which would be the first order theory, to second order theory, or we could even apply large deformation theory, which is also known by third order theory, and that would be applicable for situations where we have to account for large deformations and also large rotations. So second order theory is limited to moderate deformations and small rotations, but that would be enough for our case. When we set one of those, when we change to second or third order theory, that also goes along with the fact that we then have to do a nonlinear calculation, and therefore we can choose between different solver or iterative solver methods or iterative methods for this nonlinear analysis. But usually the preset solver methods are just fine. You can also find that when you create new models, you have already 3 different static analysis settings predefined. So we basically don't need to change these settings. We can just, or we don't need to modify the static analysis settings themselves. We just need to choose another one. But I want to keep the load case 1 with a static analysis setting number 1. So I want to still be able to calculate it to first order theory, and I just make a copy of this load case. And by copying the load case, that also means that I copy all the loads that are in the load case. And for the second load case, I now switch to the second order theory. And now we can easily calculate both and compare the results. So I click OK, and now we can switch between the load cases, and we can see, okay, for load case number 1, of course, we have still the results are active. We just calculated that. But for load case number 2, we have the same load applied here. So that was copied as well. And now I want to do the calculation of our load case 2 with taking into account second order theory. And now we get quite interesting results. So when we now like analyze the bending moments here at the column support, we see that we now have a 106.87 kilonewton meter, which is almost 70%, 7% more than what we had analyzing the same structure under geometrically linear assumptions, so under first order theory. And the delta can be explained by an additional bending moment that comes from our vertical force multiplied by the horizontal deformation of the tip of the column. So when we look into the deformations, we see that the column at the end deforms by 68.7 millimeters. This is almost or it all goes into the global x direction. And when we multiply the 100 kilonewton vertical force with this eccentricity that's coming from the transversal load, we get a delta bending moment of 6.87 kilonewton meter. So the 100 kilonewton from the transversal load multiplied by 10 meters height add up with this load coming from the eccentricity. So that's quite interesting. All right, so I also want to show you how we can directly compare, or how we can easily compare these results. So we can clone the results window. We can go to the menu bar, click Window, New Window, and now in the second step we can arrange our windows vertically. So now it splits the screen into the two windows that I have that are active, and I can now click, for example, in the first window and activate MY and the first load case, and then I go to the second window. I activate load case number 2 and activate MY, and in this way I can very conveniently compare the results of both load cases at the same time. So that's also nice in daily work, or if you want to have show multiple internal forces or deformation results of the same structure, you can use multiple windows and use this tile function to show multiple results at the same time. All right. So in this case, maybe for our example structure, the second order theory has not too much of an influence. So 7% is maybe acceptable, and maybe we could it would be sufficient in this case to calculate this according to first order theory. But the problem is, or what we have to keep in mind, is that this delta bending moment at the column end is not proportional anymore to our load. So if we now, I will now factorize the vertical load by 2.5. So I want to apply 250 kilonewton vertical force at the column tip and calculate it. Let's see how the difference now is to the original bending moment. So we now have applied a factor 2.5 to the load, but we can see that the resulting delta bending moment is now, I have to do the math, 20 by 6.8 is now almost a factor of 3 compared to the initial load of 100 kilonewton that we applied in the first step. And it, like, when we further increase the vertical load, that can even and that I want to demonstrate now. I now increase the vertical load to 500 kilonewton. And when we try to calculate this, that would even leave us with an unstable model. So RFEM gives us an error and says that he cannot find any equilibrium for this structure under the given load. So this indicates that we have an instability problem with our structural member in this case. And this is also coming from the second order theory. And I would like to now use the half hour that's left to show you how you can find out this instability load by not trying different loads and see if the model gets unstable or not, but how you can do it in a nice way using the tools that RFEM provides you. So for this task, like we want to now determine this instability load. So we have seen a 500 kilonewton vertical load is too much for this column. It will get unstable. And we want to exactly find the load that this structure can take under second order theory. So therefore we have an add-on that we can activate under base data of our model. So I go to base data and the add-ons, and I activate the structure stability add-on. That's exactly the tool that we need to fulfill our task. And with this structure stability add-on, we can perform a linear eigenvalue analysis of our model. So I will slightly modify our model. I will first get rid of the load case 2 and go back to our load case 1 that we have calculated under first order theory. I will also get rid of the 10 kilonewton transversal load, so that will just slightly change the results of our stability analysis. But maybe you see what this leads to. That would be a compressive or a slender member under pure compressive load, which is clamped at one end and free at the other end. And this would be, or that structure would correspond to a very iconic structure type, and that would be Euler case number 1. So for this problem, a slender column under pure compression, Mr. Euler already found an analytical solution to derive the critical instability or buckling load that you might already have learned from in your studies. And yeah, we want to know, see how close can we get to the analytical result using RFEM 6 and the structure stability add-on. And to perform a linear eigenvalue analysis, we can now go or edit the load case options. And since we have activated the structure stability add-on, we have the possibility now to calculate the critical load for with the internal forces that act in our load case number 1. So I open the load case options and I activate this option, calculate critical load. And then you see that I have to choose between different stability analysis settings here. I can also show you how these look like and what options you have for these options. For the stability analysis settings, sorry. So the structure stability add-on can be used to perform the eigenvalue analysis that we now want to perform. You can also do an incremental or use an incremental method to incrementally increase your load until a failure occurs of your structure. But in this webinar, I would just want to show you the eigenvalue method, because this is a very basic tool that is needed a lot and helps you to better understand your structure and how prone it is to instability. And then we have an eigenvalue method. If we choose to use eigenvalue analysis, we can choose between different methods to calculate the eigenvalues and the eigenshapes. But for most problems, the standard settings are okay. What is always interesting, or you also should always think about how many eigenvalues you want to calculate. Of course, the more you have, the more time it will take. In our case, for this very simple structure, we can stick to 4 eigenvalues and be just fine. So I leave the standard settings, and now for our load case 1, I press OK, or I press calculate. And now we can see in the calculation progress, we do one solution for the static analysis and one that was called ST1. So ST stands for structure stability. So that was a second, so to say, load case that was now solved. And accordingly, we get 2 different results now. So the results of the stability analysis, they are different results type that we can access through this drop-down menu here in the navigator, in the results navigator, or in the table. And of course, we also get the static analysis results. So of course, this also influences or the static analysis results. They are the basis for the stability analysis. So this stability analysis is done under this loading situation that we calculated here. And when we switch to the stability analysis results, we see that we first get the eigenvalues, or in this case, the eigenvalues correspond to the critical load factors here. They are presented in this table, or also accessible through this drop-down menu. And we get for each eigenvalue the eigenshape of the structure. So when we click through these eigenvalues here, either through the table or this drop-down, we see the eigenform or the eigenshape of our structure. I will now change to the colored section so we can better see what's going on with our column here. So the eigenshape that corresponds to the first eigenvalue pretty much is buckling around the weak axis of our column, which is expected. And the second eigenvalue corresponds to buckling around the strong axis of this profile. Of course, this depends on the orientation and also the section that we use for this analysis, but this is kind of what we expect from this stability analysis. The third and the fourth eigenshape are higher eigenmodes, so these are not too interesting for us now. But now let's talk about the eigenvalues itself, or the critical load factors. And these critical load factors, they correspond to the factor that you can multiply your external load with in order to get an unstable system under a second order theory analysis. So that's what the critical load factor gives you. The magnification factor, it's not very much used. It can be, for example, used to as a simplified approach to calculate second order theory internal forces from first order internal forces. So this is a simplified way to get second order theory bending moments, for example, we can apply this factor to the first order theory bending moments. That would be, for example, allowed in some cases following the Eurocode 3 for steel design. But it's not a very general factor that you will need a lot. Much more interesting is this critical load factor. So in order to show you that this would be the value that we looked for, so we have before we have done the second order theory analysis, and we saw that this column failed under 500 kilonewton vertical load. So let's again do this analysis, and so I copy the load case number 1 and perform the second order analysis. I deleted it, but I could have kept it for this step. And now in the load case 2, I want to set my vertical force to 443. So that would be the critical load factor multiplied with the external load that we set for load case number 1, which was the basis for our stability analysis. And now I just perform a static analysis for the load case 2 and see if I get an instability or not. And we can see that we can just calculate this model. Now I want to slightly increase the vertical load to 444 kilonewton and see if this is still the case. And as we can see here, okay, 444 kilonewton can no longer be taken by this structure, and it becomes unstable. So that would be that way we have verified that the critical load factor that we have found with our stability analysis gives us the critical force that leads to instability of our structure. And the nice thing, so you should basically get the same result when you do this calculation with the analytical formulas that we know from Euler. So that would be the critical actual force is equal to pi pi square divided by the buckling length square times EI. And basically this formula is used, I almost forgot to show you this because in addition to these critical load factors and the eigen shapes, we get some additional interesting results when we go to results by members and go to the tab effective length and critical loads by members or by mode shape. And here, based on this Euler formula and the critical load that is basically adopted or is equal to the internal force in the beam times the critical load factor of the respective eigenmode. So from this critical load for each member, the effective length factors are derived by the formula that I have just dropped, by the Euler formula. And what we can see here now is quite interesting. So for Euler case 1, we would use an effective length factor of 2. And this is exactly what we get from this analysis for our column when we look into the effective length factor for the weak axis and the first eigenshape. So we saw that for the first eigen value, we get an eigenshape corresponding to buckling around the weak axis, and this leads us to an effective length factor for the weak axis of 2. And the same applies for the strong axis if we analyze the second eigenmode. So this is quite nice, but of course in this example it doesn't provide any benefit, because we could also have used the analytical formulas to derive this effective length factor. But the nice thing is now we can use also the structure stability add-on to do the same calculations with more complex models. So that will be the last task of today. I will now modify the structure and build a frame from this column. So therefore, I would suggest you not to try to click along with me for this last example. Just yeah, listen what I have to say and try to keep up with the theory and the background and what I'm assessing as results, and then you can review this later for yourself. So I will now manipulate or change the length of this column to a length of 4 meters. Copy everything, including the support and the external load. So we have 2 columns now that are clamped at the end, and I will now introduce a girder between these 2 columns, and now I would have a rigid frame. Yeah, so, and for this frame, I don't know if you had ever had to do such stability analysis for such a frame, but in this case, it would not be so clear what the effective buckling length for buckling around the strong axis of this column would be like. So there are some books where you can look into some complex nomograms, and you will maybe find this effective length factor based on the stiffness of this the columns and the girders and so on. But you can also derive it directly in RFEM. So I will now do the static and structural stability analysis of this frame. And we will take a look first into the eigenvalues and eigenshapes that we get. And then we will analyze the effective length. So, okay, the first eigenvalue or the first mode, a critical load factor corresponds to buckling around the weak axis of this column. Here in this case, the girder that we have just introduced doesn't provide any additional stiffness, so we could have done the same without the girder and we would still get the critical load factor of 27.6 for these columns and for buckling around this weak axis. Then the second mode shape is also characterized by out-of-plane deformations, just that it's asymmetric in this case. And then the third eigenshape would basically now be in-plane buckling of the columns with a critical load factor of 170. So we can, just to compare, because I changed the length of the column, I want to do the same calculation or the same simulation now with the column alone, to just demonstrate or verify what I've said and see the influence of the girder and the stiffness of the frame on the results. So, okay, if we analyze the column with a length of 4 meters by itself, still for the weak axis buckling, we get the critical load factor of 27.6, same as for the frame. But for buckling in the around the strong axis, we would have a critical load factor of 79 almost. And yeah, of course, the effective length factor for this eigen shape for buckling around the strong axis would be 2. And if we again add the frame, so come back to this frame analysis, again I calculated, and now let's dive into the differences. Again, we see that the third critical load factor that corresponds to buckling around the strong axis of the beam is now much higher at 170 compared to 78. And also the buckling length for the columns we can now analyze. Of course, we have to look into one of these members and look into mode shape number 3. So this corresponds to buckling around the strong axis. And we now see that our effective length factor for the strong axis is 1.38. And this value is not very intuitive. So for this, you would, as I said, look into a specialized book. But yeah, you could also find it here. The nice thing again of this or such analysis is we can do it with very complex structures as well. We can change the loading, we can change the dimensions of the girder that would have an influence on the buckling. We could introduce eccentricities to the load and so on. Or additional support. So for example, when we fix when we apply low supports in the global Y direction in the frame corner, I will just quickly demonstrate this. So I have now horizontal supports in Y direction here. When I do now the analysis again, we will see that the out of plane buckling is now not anymore problematic or the most critical eigenshape. So when we now look into the eigenvalues, we see that the first eigenshape is the buckling in the frame plane, and out of plane is now has a much higher critical load factor and is characterized by such eigenshape, and that would correspond to Euler case number 3, I think. We can verify this by looking into the effective length factors for buckling around the weak axis for beam number member number 1 or 2, and we see that our effective length factor is now almost perfectly 0.7, which would correspond to Euler case 3. So you can see such modifications would impede the results of the structure stability analysis, and we can do all kinds of things and analyze the stability of much more complex structures and under much more complex loading situations. One thing I would like to highlight is that with this basic stability analysis that we have now performed, only the instability mode of buckling can be addressed. So if we ever want to investigate lateral torsional buckling or torsional buckling under compression, we would need to analyze this structure with 7 degrees of freedom. So we would need to add the warping degree of freedom. I know this is very a complex theory, and I don't want to bother you with this. I just want to highlight, if you want to ever investigate lateral torsional buckling or torsional buckling with the structure stability add-on, you would need to activate the torsional warping add-on, and then you could also take into consideration such instability modes. All right, then I think that I would leave it as it is now. Of course, I would like to encourage you to play around with our program and also with the structure stability add-on that I've just showed you. You can try to reproduce the different Euler cases to verify your modeling and the results, and then mess around with more complex structures and systems. Okay, so that marks the end of our journey today. I hope you learned something and found it also a bit entertaining. I mean, 3 hours can be very long if it's not entertaining. And I would also highlight that you can always visit our website for additional information, for additional input. We have a lot of nice services that can support you already during your studies, such as the GeoZone tool, where you can find snow and wind load coefficients based on a location that you can enter, or also earthquake loads. We have a very large cross-section properties library that you can assess not only through our program, but also through our website. We have extensive numbers of FAQs and knowledge base articles that you can read through and enhance your skills with. So if you have ever a question on the usage of our program, or you have an error also before, of course, you can always write our support, just an email indicating your problem, and best would be then also to put your model and a screenshot into this email so we can follow what's wrong. But before you do that, I would encourage you to just prompt your error message or the problem that you have into Google search, and behind your question just put a Dlubal or RFEM, and there's a good chance that you will find some FAQ or knowledge base article that covers your problem. Then besides the blogs that I've shown you, we have also a lot of models to download on our website, where you can get inspiration or example structures that you can use to explore the program. And then, very interesting also, all the webinars. So just as this online training, all the online trainings that we do or that we provide, they end or we upload them on our YouTube channels together with webinars where we showcase new and nice tools that we have just implemented into the program. So that's very interesting if you want to learn more about specific add-ons or the design of members and surfaces with certain materials. So I would highly encourage you to browse through this as well. And you probably also know already that you can, during your studies, get a free version of our software with a full kit of add-ons. So that's quite nice. All right, then I would like to thank you for your attention. And I hope that you take the chance and also visit some additional online trainings that we offer in the next weeks. And one last question, or what I would ask you for, if you close this webinar, you will be asked to participate in a short survey where you can rate our online training, and it would be nice if you could do that and also leave comments on what we did good, what was not so nice, how we can improve. That of course helps us in preparing the next online training. Just be sure I think you can give points for this survey, and 1 point is not good and 5 points is the best. So it's not like the grading system or the school grades in Germany where 1 is very good and 5 is very bad. It's like Amazon rating or the Google rating. 5 stars are good, 1 star is bad. All right, with this, I would leave you into the evening. Enjoy your time, and hopefully we see each other along your journey to become an engineer. All right, bye-bye.